So here's a video on how to make a mass spectrograph. Um, so a mass spectrograph comes from a mass spectrometer. That's a machine that essentially takes a bunch of atoms in, it sorts them based on their mass, and then it counts them and it makes a graph. So we're going to make the graph that is made by that same machine. All right, so here's what's going to happen. We're going to create a new document, and let's see where this is here. We're going to go to our waffle. We're going to create a new sheet. And then we're just going to create a blank one. So what I'm going to do is I'm going to go back to our barium atom. So I'm going to start off by talking about the isotopes. And if you'll remember, there was a yellow one, there was an orange one, or there were actually a couple of orange ones. There was a green, there was a blue, and there was a purple isotope. So these are all our isotopes. Next, we're going to go with our mass. And really, this could be either mass or mass to charge. So I'm going to write mass to charge ratio. In a mass spectrometer, generally, a mass spectrometer will cut off one electron, uh, making each atom or each isotope a +1 charge because it knocks off one electron. So it'll have one more proton than electron, and that'll give it a charge of +1. It also gives it some charge so that it can react with a magnet. Without that, it wouldn't really work. The atom would be neutral and it would just go straight through. So this is going to be our mass, and specifically our mass is going to be in AMUs. Generally, we only want to put numbers in the cells that we're going to graph because graphing programs like this or spreadsheet programs like this generally don't know what to do with words. So they know what to do with numbers, but not with words. And then finally, what we're going to put in here is percent abundance. Okay, and if you're wondering where the percent abundances come from, then we can talk about how many there were of each isotope. So if you'll remember, a percentage is a part over a whole, right? The part divided by the whole. And so the part is like going to be like the single isotope. And we're going to divide that by all the isotopes of that atom, which we do by adding. Right, so that's how this thing works out. So we have a part over the whole. If you'll remember, for the yellow one, it was something like we had one, the total number was 10, right? So if we divide 1 by 10, we get 0.1, which was our decimal. And then if I were to take that decimal, and I'm just going to write 0.1 here, and I wanted to represent that as a percent, then there's a little button here that actually does that for me. So I'm going to click on this, and then I'm going to click on Format as Percentage, and it'll give me 10%. So that's what I'm going to do. I'm going to fill in these percentages. If you can remember, the orange one had 2, there were 3 green ones, there were 2 blue ones, and 2 purple ones. So again, the total for each one was 10 because there were 10 bears. And then again, if I did the same thing, I would get 0.2, 0.3, 0.2, 0.2, and then I would get the same thing, right? So this is a percentage, and I'm just going to copy these over because it'll make my life a little bit easier. That's a Control C and Control V. What I can do is I can take all of these and represent them as percentages. So click that button, and that gives me the percentages. So that's where these numbers come from. But here we go. The mass for these things was 1 for the yellow one because it had 1 proton and no neutrons. The orange one was 2 because it had 1 proton and 1 neutron. The green one was 3 because it had 1 proton and 2 neutrons. The blue one was 4 because it had 1 proton, 3 neutrons. And then the last one was 5 because it had 1 proton and 4 neutrons. So that's where the mass comes from. And then we have the percent abundances. So I'm just going to take these things and copy them over because we know where the percentages come from. I'm just going to hit Control C and then Control V, and it'll copy my percentages over. So these are my percent abundances. The percent, again, is a part over the whole, or in this case, a single isotope over all the isotopes. So here I had 1 was my part, 10 was my whole, so 1 over 10 times 100 gives me a percentage. So now what I'm going to do is I'm going to take these things, I'm going to click and drag on all of them, including the titles, and I'm going to insert a chart. So the chart is right here, so I'm going to do that again. I'm going to highlight all of these, so including my titles and all the data, and I'm going to go to insert here. It's like the fourth one from the left. I'm going to go to insert, click that, and then I'm going to go down here below timeline, right above pivot table is a chart. And what I'm going to do is I'm going to go with a column chart. So if it's not automatically selected, you can go there and you can look at all the kinds, but column chart is right there. I'm just going to go with this one because it's already been selected for me, and I'm going to close this out. So what this gives us is our percent abundance here versus our mass. And what you're going to see most of the time is instead of this being mass in AMUs, and while it is, this is really our mass to charge. And our charge is +1, so this is really like the mass divided by 1, which is just going to give us our mass again. But on most mass spectrographs, that's what you'll see. And what I'm going to do is I'm going to change the colors here. You don't have to, but I'm just doing this specifically because I want you to see exactly how this matches up. So I'm going to double click on this, and I'm going to change the autofill color to yellow. You don't have to do these things. I'm just showing you so that you can see exactly where they line up. All right. And so now you can see, I'm going to change this to mass spectrograph of barium. This is my mass spectrograph of barium now. Okay, I'm going to move this over to the side here. And here you can see that these are my percent abundances. The green one was the most abundant at 30%, so it's the highest in the column. It has the tallest column. And here we can see the masses, 1, 2, 3, 4, 5. And again, these things come from the number of protons and neutrons combined. So they all have the same number of protons because they're all the same kind of atom, which is barium. But we can also see that they have different masses, so that's what makes them isotopes of each other. And so here we can see that our yellow isotope was the least abundant. The orange, the blue, and the purple isotopes were all equal at 20%, and then the green one was the most abundant. So why do we do this? Why do we have a mass spectrograph? Well, the reason why we have it is really so that we can look at the data more easily. And so with this data, what I can see is that on the low end, my mass for my average atomic mass for all of my barium should be 1. And on the high end, my mass can be 5. So when I look at my average atomic mass, it's going to be the weighted average of all 5 of these. But this gives me a low end on what the average atomic mass, could be, and what my average atomic mass could be on the high end. So really what it should be is somewhere in between these. And what I can think of this as a seesaw. Okay, so if I think about these as a seesaw, then where can I balance this? If I were going to balance this, let's say these were 5 objects on a plate or on a platter, and I was carrying this, where would I carry the platter? Where would I put my hand in order to balance all of these? And so what we can see is that here's like the middle. On the left, I have a little bit less. So the orange and yellow are a little bit less. And I can see that the blue and purple are a little bit more than the yellow and orange. So I wouldn't balance it directly in the middle at 3. It's actually skewed a little bit more towards the right. So when I look at this, what I get is a mass that's slightly higher than 3. Because again, this percentage is a little bit less, so we count it a little bit less, right? It's only 10%, where the other one is 20%. So if they were all the same, then we could say, well, I'll just take the average, the mean, and I'll just add all 5 numbers up and divide by 5, but I can't do that because they contribute different amounts. The percentages mean that they contribute different amounts, and so I have to factor in that yellow has a little bit less. It has a smaller percent abundance, it contributes a little bit less. Green contributes a little bit more because it has a higher percent abundance. And so when I do all of that, if I'm trying to balance this, I'm going to balance it just slightly higher than 3 because, again, the blue and purple contribute slightly more than the yellow and the orange do. And so it's just going to be slightly higher than 3. And if we go back to our data, we would see from the last video that our average atomic mass was equal to, and I'm just going to write this in here, 3.2 AMUs. That's what our average atomic mass was. And if you go back to the last video, you'll see that that's the case. So this is where the actual average atomic mass is. This is where the weighted average is. And this is where we would expect it kind of to be based on this spectrograph, right? So again, if this is right here in the middle, this one contributes the most. We can see that the blue and purple contribute just slightly more than the yellow and the orange. So we would expect it to be just slightly higher than 3, and that's exactly what we get here. All right, so this was barium, which is pretty good, but we also want to do this for another one. So what we want to do this for, and I'm just going to copy these over just so I don't have to write them again. And what I'm going to do is I'm going to write in the isotopes of magnesium. Again, this was from our last video. This was magnesium. Magnesium has 3 isotopes. Not everything has the same number of isotopes. Some things only have 1 isotope, some things have 2, some things have 3 isotopes, 5 isotopes, 7 isotopes. The numbers can vary, and so the total will depend on how many isotopes there are, but I'm just going to change this. It's easier than writing it all out again. So I'm just going to slightly change those. And then we have the masses. So the mass to charge, or the masses, again, the charge is usually +1, because usually a mass spectrograph knocks off 1 electron, making the whole atom or isotope positively 1 charge. So mass divided by 1 is just going to give us the same mass again. I'm going to write these things in here, 23.985042. And again, I only want the numbers. I really only want the numbers in there, because once we get to letters, then it thinks that this cell is a word, and spreadsheet programs just don't know what to do with those things. So I'm going to finish typing these in here. All right, so I have my masses in there. Again, these masses come from the fact that neutrons have a slightly greater mass than protons do. So this is why it's not exactly 24, not exactly 25, not exactly 26. Remember, the mass comes from the number of protons and neutrons. But because neutrons weigh just slightly more than a proton does, it has just slightly more mass, then these numbers are not exactly 24, 25, 26. But they're pretty close. And then we have our percent abundances. So again, I'm going to write in the decimal. And these are the same ones, if you're wondering where I'm getting these from. These are the same ones we established last video. These things ran through a mass spectrograph. So that mass spectrometer, the mass spectrometer weighed all of them, got the mass of all of them, and then it sorted them and counted them. So it said, here, look, here are a bunch of magnesium atoms. They come into the machine. It says, oh, this one weighs roughly 24, this one weighs 25, this one weighs 26, and it sorts them. And then what it does is it counts them. And then it knows how many it counted, and so it takes the percent. And again, that's the part over the whole. So here we can see, this is roughly out of 10,000, something like that. So 7,899 would have been magnesium 24. roughly 1,000 would have been magnesium 25, and 1,101 would have been magnesium 26. And so altogether it's out of 10,000. So this one's like, so that's how we got those percentages. And I'm actually going to change these two percentages just by clicking that button there. And then I'm going to do the same thing that I did before, right? Which was to highlight these things, highlight all of my data. And then I'm going to go to insert again. I'm going to go to chart again. And here's what I'm going to get, right? And again, this mass is really not just the mass, it's the mass to charge ratio. Sometimes you'll see this as M /Z for mass to charge. But again, the charge is just 1, so you're really dividing by 1. And so it's really just going to be equal to the mass. Again, we have the percent abundances. And what I'm going to do here is I'm going to change some of these colors. You don't have to. The only reason that I'm doing it is so that it's just slightly more visible. So it's just a little bit easier to see the differences here. And I'm going to make this black just so they all kind of stand out a little bit from each other. And I'm going to say that this is the mass spectrograph. Again, you don't have to do this, but just so you can see where these things come from, of magnesium. All right, and so I'm going to move this down here. And now we have R2. So you can see how we got the mass spectrograph of barium, right? You can see how each one contributes to something, contributes to the whole. And then here we can see that magnesium 24 is really the most abundant, so it's going to contribute the most. So if we think about balancing this on a seesaw, or if we think about the upper and lower limit, so the lower limit is going to be roughly 24 AMUs. The upper limit on what our average atomic mass could be is going to be roughly 26. So our average atomic mass is going to be somewhere between the low end and the high end. And how we can figure that out without math really is by saying, well, again, if these three things were on a platter, where would I hold the platter so that these things could balance out, so that it wouldn't drop the platter? And really, we'd have to hold it closer to the isotope of magnesium 24, right? Because this is where most of the contribution is coming from. And so if we look back to what magnesium is, the average atomic mass of magnesium is going to be 24.30505. Usually this will get shortened down to 24.305 or 24.31 when you round it. So it'll be somewhere in this range, right? And these will all be in AMUs. So that's exactly what we would expect, right? We have 23.98. They're not all magnesium 24, so that means magnesium 25 and magnesium 26 also make a contribution. They make the average go up a little bit higher, but not by much, because we can see this one's only 10%, this one's only slightly higher at just above 11% contribution, but this one's close to 80% contribution, so it's going to be closest to this thing. So it'll just be slightly higher than 24 when I average them all together and I include their percent abundances. Hopefully this video makes sense. I hope you enjoyed it. Have a good day.